So just mentioning one of the versions of GA that has been very successful is differential evolution, or DE, which is very fast and is real valued, and it works with the difference of two values that are being optimized. I guess you heard about that a little bit in the last lecture or tutorial. So I don't want to go there. I will not go there. But looking at this, I want to talk about another idea which is very closely related to this, and hopefully we can, within 1 hour, get some insight into that. So I want to talk a little bit about opposition-based learning, because that can be applied basically on any type of AI technique. So idea is use opposites for better or faster learning / optimization. So use opposites. So my first question is, what do you mean with opposite? What is opposite? So if this is a space and I lose my cell phone in this space, so this is my cell phone, I lose it. And then I want to start do sampling, and how do I find my cell phone? So the question is this a space, this room in E7, is it E7? Is it the city of Waterloo? Is it Ontario? Is it Canada? Or is it Milky Way galaxy? So how big is the room? Tell me. If it is this room, any solution will do, any problem will do. It's not a big deal. Even if it is 7, even if it is Waterloo, we can do that exhaustively. But if it is Ontario, it becomes difficult. So Canada, oh my God. Milky Way galaxy, okay, forget about that. You can't do this. I'm assuming you have one solution, one location. So one idea is you make a guess, you make a random guess. I don't know, you make a random guess here. And then you try to find it in your immediate proximity somehow. So another idea is, okay, if you make a guess, x, can you tell me what is the opposite of x? So if this is this axis value and this is this axis value, what is the opposite of this location? I don't know. If I look at the symmetry, I would say here the opposite would be here, and the opposite of this point, I don't know. I have no idea. Maybe here? So the opposite of x, which I put a brief sign on top of it, would be there if you accept my just intuitively defined, not very solid definition of opposite. So you make a guess here, and then you search. At the same time, I make the opposite guess and search here. So you are searching in that corner. I intentionally go to that corner. Why should you do that? Well, it doesn't make sense to search very close to you. You are already looking here. So I try to go as far as I can away from you. And then if you can, with some sort of measurement, you tell me which one is better. So if I cut this in half in this dimension and cut it in half in this dimension, if you can tell me, is x better or x brief is better? Which one is better? You have some measurements. You have some error function, some fitness function, some reward function, right? You are using that already. So you can evaluate the goodness of a solution. Yes, we can. Most of the time we do. Okay, so if you realize that xbrief is better, that means you get rid of this half. Wow, that's a drastic decision. You got rid of half of the Milky Way galaxy. Okay. So which means now I'm working in this half, and now things have changed. So now the opposite of xbrief, where is the opposite of xbrief? Because I cannot define it here. The opposite of xbrief will be here, right? If I stick with my symmetry, this is xbrief brief. And then I look, was my initial opposite is better, the opposite of the opposite. But the opposite of the opposite is not x, because the search space has changed. So the interval has changed. Okay, I realize still my opposite is better, so I get rid of this part as well. So now I have only that left, and now here I define the opposite of opposite of the opposite of this opposite, so which is, okay, so here I go here, it probably is somewhere here, right? So this is the x of opposite, 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 so the third opposite. So I don't have a terminology yet, so I'm struggling to make a point. And you look which one is closer. Of course, you see that this one is closer, so I cut this in half, and this goes away. So this seems to be like binary search. If your data is sorted, but my data is not sorted. So no, yeah, it's search. And actually the behavior will be logarithmic. And if it works, I would love that, because I love everything which behaves logarithmic. So, and then you can continue, and you see that if I continue, you will cut this in half. And the opposite is here, and it's already really close. There you go. You hit the solution. So which means you are jumping from this side of Waterloo to the other end of the Waterloo. And you say, okay, the west end of Waterloo does not contain any solution. Don't search there. If you can do this, this is going to be fantastic. But if you do this, first the question is, excuse me, what is opposite? Well, that's a difficult question. I don't want to go into nature and say, I don't know, that the opposite means this and that. We have atoms, we have electrons and positrons, they are opposite. So the concept of opposite, we have yin and yang, this is philosophy. We have night and day, we have male and female. Oh, yeah, I know. In the nature, opposites are everywhere. So opposites are things of the same nature, but distinctly different. They're both numbers, in our case, but with respect to their proximity to the solution, one is very close to the solution, one is very far from solution. Okay, I can live with that. So for any given x coming from interval AB, the opposite of x, namely xbrief, can be given as, so xbrief is a plus b minus x. Okay, that's easy. So if you are working between 0 and 100, the opposite of 20 is 80. Okay, but what does that mean? Well, at the moment, nothing, because we have not defined an output function. What do these numbers do? So I need to do that. So, but if I know the interval, I can define a simple symmetry-based opposite. Okay. So what is the idea of learning? So idea of opposition-based learning. So given an unknown function f of x. And don't forget, x here is a vector that I'm not really declaring yet, because we don't want to work with functions with one variable. Given an unknown function f of x with an evaluation function g of x. So I don't know f of x. That's the unknown relationship between in and output that we said from the beginning. We don't know that function. But I have an evaluation function. What is that? Error, fitness, reward. Everybody has one of those. So you get one of those, work with it. So with an evaluation function g of x, we for every guess x and its opposite x brief, we continue with x if g of x is greater than g of x brief. Of course, if g of x brief is greater, we will continue with x brief. Right? So sometimes the initial guess was bad, its opposite was good, so we go with opposite. Sometimes the opposite was bad, we went with the initial guess, so we don't know. It's a matter of luck. I lost my cell phone here, you position yourself there, you are lucky you find it, I'm looking there, so I will be the stupid one. Nobody knows. Is the initial guess better or its opposite? But if that's the opposite of here, this is the opposite of that, so basically there is no difference between x and opposite x, right? So who cares? Both are numbers. Yes?
I wonder if we don't know the black dots at all, then how do we get the evaluation?
How do we do it in neural network? We don't know where the cell phone is. We don't know the location of the solution. But we have a means to move toward it, which is gradient descent. In reinforcement learning, we don't know where the best solution is for the elevator. But we have a means to move toward it, which is the reinforcement signal, reward and punishment. That evaluation function doesn't change. It has nothing to do with the method that you apply. So if you have lost somebody in a natural disaster, and you only get the cell phone signal of that person, we don't know exactly where he is, but we are following. And so, okay, here it's get weaker, weaker, go back, stronger, stronger, stronger. Okay, weaker, no, go this way. So you have an evaluation function, but you don't know exactly where the solution is. So, okay. I have no idea where you're going with this. Okay, it's saying if you want to solve a problem, f of x, which is unknown, but you have an evaluation function g of x, you have error, you have reward, you have fitness, at any time when you make a guess, x makes also an opposite guess. Use my simple formula, okay? And then see which one is better. X is better or opposite x is better. And continue with the one that is better. Okay? So just out of curiosity, how something like this would work with neural networks. Oh, okay. So example. So there is an artificial neural network given. So containing some weights, right? So these are WIs, your weights. You create the opposite artificial neural network. So I put a brief on top of all of this. And you have your opposite weights, which your opposite weights are A plus B minus WI. And A could be 0, B could be 1. Simple case. So which means what? Which means what? We did this experiment back in 2004, perhaps, 2003. So you create a neural network, random weights. You make a copy of it and turn all weights in opposite values because you know the weights are restricted between a certain number. You know your logistic function. My function goes between 0 and 1. So the opposite of 0.2 is 0.8. We may still argue about the concept of opposite, what it means to be opposite. Okay, we get there. Okay, just stick with me. So, okay, then I have two networks. First of all, as a programmer, I freak out because managing two networks in memory, if they are deep, that's a nightmare. But I'm listening. Okay, I'm listening. So you make two networks, calculate the error for this one, calculate the error for this one. Which one has the lowest error? This one. Scrap this one. Continue with this one. Go do backpropagation. Weights change. Create the opposite network again. Which one has lowest error? This one or this one? This one. Okay, scrap this one. Continue with this one. So continue working on the network with the lowest error. Problem: memory intensive. It cannot drag two networks all the time. Do I need all the time? Most likely not, because down the road, at the beginning, everything is a mess. Weights are random. So you're searching literally in Milky Way galaxy if you have 500,000 hyperparameters. So everything is random, even after all tricks. Okay, so but after what? After 10 episodes? Things are taking shape. I don't need to that switch anymore. Maybe not. Maybe just I do it at the beginning. So perhaps only meaningful at the very beginning. Maybe. Maybe just at the beginning. Okay. Okay. I want to try this, but this is hard. Neural networks are not easy to work with, so maybe I apply it on something else. What about reinforcement learning? Well, we said that the easiest way of implementing a reinforcement learning agent is the tabular implementation. So we said that you have really long table in the Q implementation, and then you have your A1, and you have your A2, and you have your A3. Let's say I have only 4 action, and I have my state number 1, state number 2, and I have n states. And this is an extremely long table. Then I come and take a look at the specific state S sub I, and I'm taking an action, and I get certain reward for this action. So I get reward because I took action number 1 for state I. So if in this is state, action 1 is good, what do I know the opposite action? What is the opposite action? Send an elevator up. The opposite action is send the elevator down. The robot goes to the left. The opposite is robot goes to the right. The simplest, easiest way of defining it. So if A3 is the opposite of A1, you have to figure that out. Is action number 3 the opposite of action number 1? Then I will give it the opposite reward or punishment. Okay. And then I know that S sub j is the opposite of S sub I. Do you know that? I don't know, maybe. Maybe I'm lucky and I know what is the opposite of my state. The opposite of actions is much easier because the set of actions are simple, are clear. We know that it's under control. But we know that the state space is gigantic. So maybe I know it. Okay, if the action 1 was good for the state I, it should be bad for its opposite state. So I give the opposite here. And vice versa. Then the action number 3, which was bad for this I, should be good for the opposite one. So I give the R here. What does that mean? I made one change, but I added 3 values instead of 1. This was the original. So we said that reinforcement learning is about taking action, interaction. That's also taking time. That's also super fast. Like genetic algorithm is also slow. So, and we said Watkins told us that reinforcement agents converge, give you that policy if any spot in this table has been visited multiple times. So the key to a fast convergence is how many times I can update. So I get one observation and made 4 updates for one observation. If I can do this, that's going to be amazing. Yeah, tiny problem. Do you know the opposite actions? Do you know the opposite states? Sometimes we do, sometimes we don't. Because you have to be sure. So you have to be sure that it's really the opposite. If it's not the opposite, you are giving conflicting information to the agent. You are destroying the policy that it's trying to build. So the nature of oppositeness has to be really crystal clear. Otherwise, we will be in trouble. Okay. So you are not encouraging me, are you? Yeah, I just want us to be cautious. So, okay, so we just talked about evolutionary algorithm. What about evolution? Can evolution benefit from opposites? I don't know. I'm just trying to fit this idea of whatever opposite means into everything because I want to publish papers. So, okay, so you were talking about bits and bytes and mutation changing one bit. How about we flip all bits? So total mutation? Yeah, total mutation. So now you are going totally insane. Yeah, so why not? So if I have my chromosome, and I do a total mutation, then I get 1, 0, 0, 1, 0. I get my anti-chromosome. And here I had my counteraction. So you can come up with your own terminology. So if I flip everything, I get a totally different chromosome. That's dangerous. We said if you just flip a bit, that could be dangerous. Yeah, but I'm not continuing with this. You're not? No, I said we only continue with this if it is good enough. Oh, so that means many times you generate opposite and you're useless. It could be. Yeah. So there is an overhead for using this. If this idea has any merit, it has an overhead. You have to generate the opposite. You have to evaluate for x. You have to evaluate for opposite x and see which one is better. That's not handy in some cases if I'm dealing with 500,000 parameters. But evolution may be reasonable to apply this. So some people went through some problems and applied this on and built opposition-based differential evolution, or ODE. this has become, nobody could guess, but this has become the most successful implementation of idea of opposition. So many people applied that, oh, it's really nice. And then the question comes, okay, why is that nice? Why does it help in evolutionary context, but it does not respond well in other contexts? Well, the research is not done properly yet, but it seems that its benefit is in evolutionary part. Okay. So first of all, I want to go back to what is opposition. And I want to challenge you. And maybe this is the reason that you may not be very successful with neural network. You are a little bit successful for this one. What is the opposition? So if I look at function, if I look at the function which is linear, then this is A, this is B, and this is my x, then of course x brief, which is A plus B minus x, is perfectly all right, because this is a linear function. So opposition, the way that I gave it to you, the opposite of x is A plus B minus x, and A and B being the minimum and maximum of universe of discourse. Probably will give you immediately something if you have a linear function. Yeah, but my problems are nasty and nonlinear. Okay, that's the reason that most of the time that overhead that you pay for generating opposite x and comparing them is useless. Why? Well, because the function that you have is something like this. So if you have this, and I grab this, what is the opposite of that guy? So based on x plus, so based on, again, this is A, this is B, this will be opposite of x, which is A plus B minus x. So this would be the opposite of x, which is clearly not the case if I look. Why? Because low x gives me low output, high x gives me higher output, because that's a linear function. So if I have low x, I have to go, actually my opposite here should be somewhere here. Sorry. Should be somewhere here. But it's not, because this function is not linear. So can it be that if your function is linear, then you say x opposite is A plus B minus x, whereas x belongs to A plus B. But if it is nonlinear, okay, what about if nonlinear? How can you define opposite if your function is nonlinear? Well, if you have a nonlinear function, basically you get a set of x sub I such that y sub I is y min plus y max minus y belonging to y min and y max. So which means you cannot determine the opposite unless you look at the output. So my x becomes an opposite if that opposite generates the opposite output. Again, we don't know f of x. That's the challenge. So which means what? You can define opposite here in this region, because here I have a piecewise linear function. I can define it here because I have piecewise linear. I can define it here because I have piecewise linear. I can define it here because piecewise linear, and I can define it here. So, but I'm assuming fundamentally that it's going like this, which is, of course, giving me a lot of error. So if I could, with low expense, estimate the output, then come back and adjust, I should be actually okay. Okay. Well, let me challenge you. How about randomness? You were just praising the God of randomness. Yeah, what about randomness? Well, you're saying you use opposite, and you get x and you get opposite x. How about I do 2 random guesses? Won't I be able to beat you? So, scenario 1, x1 and x2. These are random guesses. Random guesses. So I make 2 random guesses at the same time because I like your idea that you have 2 alternatives and you look which one is better and you continue with that. I like it. But I don't buy into your idea of oppositeness. I do it with random numbers. Why not? Random sampling is a very powerful thing. Yes, you can do that, sure. Another scenario number 2, x1 and opposite x1. Okay, now we have competition. Okay, so I run this 1 million times, and I run this 1 million times, and see who would win. Randomness or oppositeness? First of all, what is special about this? So these are independent from each other. If your random number generator is good, x1 and x2 are independent, which is the whole power of randomness, because we can generate them independently. So we can play with the structure. But x1 and opposite of x1, they are negatively correlated. Doesn't matter how you define them. The negative correlation may be low or may be big. So if I'm applying this on a nonlinear nasty problem, the negative correlation will be low. If I go this way, it will be high. But there will be negative correlation. So, okay. So the question is it that the g of x1 and opposite x1 is better generally, or the g of x1 and x2? So, and we found that this is better with 12% higher probability. Which, if you tell it to a statistician, he or she will tell you, yeah, I sort of expected that. So, what? Now that I have good results, you expected that? You were just rejecting my paper. Yeah, I expected that because they are negatively correlated. We had the concept of antithetic variates in the statistics. We know that negative correlation can bring miracles. The only question is this. Are they really negatively correlated? And how far are they negatively correlated? So that person, my friend, is searching there for my cell phone, and I'm searching there. Am I really there, or I imagine I'm there? Actually, I'm here, close to my friend. And in a quantum world, I think I'm there. So if you assume the system, the problem is linear, you are not there. You are here. So you don't get much different result from that person. 90% of your overhead is wasted. So you have to make sure that you have really negative correlation. which is a really fancy business. We prove this mathematically, 12% of the case. And you can run an experiment. Run this a million times, run this a million times, you get close to 12%. You measure how many times this is better, how many times that's better. Which is very, very strange when you hit something that you didn't know. But then somebody comes along and says, well, actually, we know that. So this is antithetic variates. You call it opposite. It's just antithetic variates. Doesn't matter what we call it, but how can I use it for the idea of learning? OK. Yes?
Is there any proof that shows the random selection is kind of like a lower bound of opposite selections?
If random selection is generally a lower bound of opposite selection?
Like, can we prove that like opposite selection is always better or equal to?
No, nobody can. It's all about probability. So this is correct with a probability of 112%. So 12% high. In 12% more cases, this is valid. So if this is, we cannot really certain say that. And the problem is, again, so how do I find that negative correlation such that we can go ahead and use it, actually? OK. If we go back to the GAs, let's say on images. If I get an image with some sort of objects in it, I have to go back to my kindergarten drawing. So if I have an image with some object, and I want to now, I am excited about evolutionary technique, and you told me about differential evolution, which you have not described, I will look it up. And maybe I can play with the idea of oppositeness and see what happens. But OK, I want to do something exciting. How do I apply genetic algorithms on something like images? So the first question that comes to mind is, what is your fitness function? What is the fitness function? So then I would ask, if you ask me what is the fitness function, I would ask you, OK, what is the task here? What is it that you want to do with this image? And then you would say, well, I want to segment the image. OK. You want to segment the image. Which means maybe you want to extract the river, right? The river is sort of blue, the sky is blue. So you are interested to extract this guy, but I'm guessing that you will also get this guy because these two have certain color, so you have to do something about it. OK. So I want to apply that on, solve that using genetic algorithms. So what is the fitness? How do I segment? So a segmented image, in this case, is binary. Is a binary image, right? It's black and white. Should be white for here for the river and black for everything else. Then you have segmented the image. Then you know pixels that belong to the river are pixels that are white in my segmented image, which is your label image, which is your mask. So a segmented image here in our case is a binary image. A binary image is an image with highest contrast. OK? You can always increase the contrast of an image. We have formula for contrast of an image. So x minus min divided by max minus min, that gives you the contrast, sort of. So, and if your min and max are close, your histogram is right in the center. Everything looks gray, no good contrast. So if your min is 0 and your max is 255, the image just jumps at you. Sharp, full of colors. So I can understand that, the concept of contrast. So, but if the contrast goes really to the extreme, the highest value of the contrast, so basically everything gets dark, 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 and this gets bright, 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 then I may be close to that perfect binary image that I'm after, the segment. Okay. So can I say that the fitness is the contrast of the image I? And then I look for a formula in the literature for contrast. How do we measure contrast? Yeah, signal processing 101, just grab a book, search it somewhere, find the equation, because we know how contrast look like. So now I have a formula for my fitness. I want to maximize the contrast. Okay, good. Wait a minute, but what are my chromosomes? If the contrast of the image is my fitness, okay, I will find that equation. That's not a problem. But what are the chromosomes? Well, you need to do some homework, because again, this is the part that maybe neural networks are more handy than evolutionary algorithm. So what are chromosomes? So you need a function. So you determine that contrast is a function that you can put into an equation. So, but I'm assuming if you put the actual value of the image into it, it gives you a value. But you want to manipulate that value. So what would manipulate those values? You need a function with parameters that change the contrast. Okay? The contrast of the image is every single value G sub I, G sub J, so all the pixels, minus the minimum value that I have in the image divided by maximum minus minimum. I just saw that on Wikipedia, so I start with this because I didn't take image processing, so I have to watch some YouTube videos this week and figure it out. Well, but okay, that's fine. I start with this. Look, I'm not being derogatory. I always start simple. You cannot go with the most complicated, sophisticated thing. That will kill you. I want to establish the skeleton of a simple thing, get it up and running. I'm a hopeless engineer. Get it up and running. Get it to work. Then we will optimize it. Okay, I get this, but these are the values of the image, and this is the minimum and maximum of the image. There is nothing to change here. Yeah, you're right. So what about I put this in a bracket and take this to power of alpha? Where do you come up with alpha? I made it up. I made it up. Okay. Okay. But if you do this, it will find a value. So basically, you give alpha as a single value for your chromosome. Your chromosome will be the binary codes for alpha, whatever the alpha is. But alpha here is a value between 0 and 1. Well, that's going to be tough. That's going to be tough. I want to make it a binary. So maybe I discretize it and say 0 and 1 is 0 to 100. OK, I can work with that. And then 25 is basically 0.25. I can make that conversion. That's not that's not difficult. OK, but still, if I do this, it will change this alpha. So alpha will be my chromosome. And it will try to create, create a population of 50 alphas randomly, which would be 50 numbers between 0 and 1. And then see which one is fit. What is fit? Which one of them creates the highest contrast? This. Okay, but is this the only condition? Because I may get the highest contrast, but there's still a lot of garbage in the image. Okay. So I have to put some constraint on this. So if I have a perfect image like this, and there is no garbage here, and I just want the river, I don't want anything else. So beside of the contrast, I need something else that constrains the operation. You see, this has nothing to do with AI. This is domain knowledge. If you have not worked in the image processing, you will have a tough time. So if I'm new in that domain, I have to go grab the knowledge. But I'm sure if you are doing something, it is right in your domain. So this is the part of analysis that you say, how do I make this problem fit the only solution that I know, the only hammer that I have, which is evolutionary algorithm, if I don't know anything else. So I have to find a fitness function to work. Okay. Okay. Let me think. So maybe, so if I have an image like this, and I have, let's say I have the perfect river like this, but I have also some garbage here. Because if you do this, there will be noise, there will be some stuff, so you will not generate a clean image with just the river. It will be a lot of nonsense in it. Okay. If I calculate something else that would be maximum just in case the river exists and nothing else, that something will not become maximum if other stuff are in the image. Like what? For example, like compactness. So compactness is the area of an object divided by the perimeter of an object squared. What is the most compact object we know? What is the most compact object we know? Circle. That's why Mother Nature makes everything round. Most compact object. Anything else has less compactness. So if I have garbage the image, if I calculate this, the compactness of this river will not be as high as the compactness of a circle. But definitely with this garbage, it will be even less. The area divided by perimeter, you add to that. So, okay. I could add this, which means if I increase the contrast, then I get binary image. I have to go in and calculate the area of those objects, which is easy. I just count the white pixels. That's the area. The perimeter will be a little bit more difficult. So for perimeter, I have to find this line, this contour, and then count the pixels on the red line. I have to find this guy. I have to find this guy. I have to find this guy. Oh my God, I have to do a lot of stuff. Then I have the perimeter power 2. And since this is perimeter squared, these numbers will increase, my compactness will come down. You see, this is not something that you can develop if you are not in the field of computer vision. Because I'm just throwing at you a lot of domain knowledge. That if you are not an image processing expert, nobody can expect that you know those stuff. You have never heard of compactness. Okay, that's a problem. But I'm showing how we go step by step to design something. Okay, so this should be maximum, and this should be maximum. Okay, so then my fitness function will be G minus min over max minus min alpha, power alpha, plus area over perimeter squared. So now I can control it. But still my solution is very simple. Still, the only thing that I have to put in the chromosome is the alpha. which definitely would make my algorithm too simplistic to solve the problem. But at least it cannot just go insanely large and make everything white. Highest contrast, everything white. No, highest contrast, but give me the river. So if you give me the river, again, the contrast, we can define it for a specific color, blue. So if you give me just the river, then the compactness is very high. So this becomes really high. The fitness becomes big. Then hopefully my algorithm will work. And then this would be my alpha. So, and I grab certain number of bits. Alpha, again, I cannot encode between 0 and 1. I convert it to 0 to 100. And then how many bits do I need to encode numbers between 0 and 100? I don't need 8 bits. I don't need 7 bits. 6 bits? 5 bits? That would be enough. So all those things need to come to play to define a fitness function. And now I have my chromosome. Now I can do all those things. You see, I just wanted to make the point, look, evolutionary techniques are different from, for neural networks, you have a framework that is defined. We use this. Actually, everything is systematic. For this guy, every time we have to do this from scratch. And one other bad thing about evolutionary algorithm, as if I'm getting rid of them. So one other bad thing. What is that? So let's say I do this, and I get the river, right? A big problem. So another disadvantage of GAs. Given another image. So somebody gives me another image. I apply my GA on this, and I sort of get it right, and I impress people that I can extract the river from the image and say, this is the river. I can recognize river. If you can recognize the river, if you can show that this is the river, does anybody care that you did it with genetic, or you did it with fuzzy, or you did it with Bayesian, or you did it with neural network? Nobody cares. Because that app that does that will get downloaded 500,000 times. It doesn't matter. So, but now I give you another image and say, okay, now look, now this is the house. And the river is this. You just killed my method. Because I have to run the sluggish, slow evolutionary algorithm again. What does that mean? Do I have to put input to neural network again? Yes, but neural network, after training, you don't run it again. You just call it. Wait a minute. What? When I train a network, training is done, I bring it, and I apply it on any image. And it's super fast. It doesn't learn anymore. It already learned. In evolutionary techniques, there is no such a thing. You have to run the optimization every time from scratch. This is the fundamental difference between optimization and learning. When you optimize, now I get a new instance. This was an old instance. I optimize it. I gave you the river. Now I have to do it for this image. Evolutionary techniques do not generally save anything after the optimization that they can reuse. There is no weights. There is no table with actions and state values. There is no rules like fuzzy system. It just does the job for this guy and say, here. And you give me another one. 5,000 generation, 6,000 generation. I have to do it again. GA has to be rerun from scratch to optimize the fitness function again, this time for the new image. Oh, that's a problem. Oh, that's a problem. As bad and as nasty neural networks can get for training and put a lot of pressure on us getting resources for training them, when they are trained, they are good boys, fast. So they are real time, deterministic. You can calculate. So for data, I put the data, I have one GPU, 1080 Ti, it gets 200 milliseconds to get response from the neural network. Not going to happen here. You have to do it again. You have no idea how many generations takes for this image. Another image comes, you have to run it again. Optimization is a task-specific operation that has to be rerun again and again. Optimization generally does not save anything that you can reuse, like neural networks, like reinforcement learning, like fuzzy systems. Again, I'm talking about optimization in the most general way that anybody can talk. And recent research is going in the direction that there were recently published a paper, if I find it, I will post it on Learn. There were recently published papers that evolution was able to beat neural networks in accuracy for specific applications. They are very capable, extremely capable. But they have this very problem that you have to rerun them again. And the research is looking into the so-called innovization, how you can innovate by save it and use it again. So people are working on that. But generally, the canonical JI, you have to run it again and again. So I don't want to go more than this. We are only 7:50, so you have to stop. So we will hopefully, you will get quiz number 5 soon. I will let you know what this is about. And we will continue next week with the Bayesian inferencing.